Hello, my name is Hocke and I will talk about denoising methods in fMRI and in particular in the low frequency. Why should you be interested in the low frequency domain in fMRI? Because we are looking for the signal resulting from neuronal activation, and no matter how fast your stimulus is, your signal with fMRI is limited to the slow hemodynamic response. You can think of the hemodynamic response as a kind of low-pass filter, and so you will never see a signal related to neuronal activity that is faster than this low frequency range. And this is why we're so interested in this range. We've established that part of the signal in the low frequency range is neuronal. However, part of the signal is not neuronal. And this non-neuronal signal will confound your detection of the desired signal, and therefore it is critical to account for it. The problem is you cannot cut it out or filter it because it is in the same domain as your indirectly measured neuronal signal. And this problem is a little bit more manageable in traditional fMRI, in which we have a time-locked response to our stimulus. However, in resting state, we don't look for a stimulation protocol correlation. We look for coherence between areas. So we look which regions are correlated and therefore neuronally function together. And because of that, it is even harder to separate the neuronal from non-neuronal signal. So what are these omnious non-neuronal LFOs I'm talking about? We know they are spontaneous hemodynamic variations. We know they're highly prominent in functional measurements of both fMRI as well as functional near-infrared spectroscopy, which I will get later to. And they are centered around 0.1 Hz. However, that's pretty much all the information we have. There are various names for these non-neuronal LFOs, and even the specific frequency range varies somewhere between 0.01 and 0.2 Hz depending on which paper you look at. There's also not much known about their origins or functions. However, there have been several suggestions, including vasomotion, which is the oscillations in vascular tone, thought to be generated within the vessel walls, changes in arterial pressure and changes in carbon dioxide, as well as recently gastric slow waves. In addition, we have variations in respiratory volume or variation in cardiac rate resulting from systemic modulations of cerebral blood flow. In fMRI, we have several denoising methods to account for aliased signals, meaning signals in higher frequencies which are not properly sampled, as cardiac at 1 Hz. To account for the non-neuronal low-frequency oscillations, the golden standard of fMRI denoising has been the cardiac and respiration variation model I just showed before. These methods were spearheaded by Dr. Chang, Dr. Glover, and Dr. Byrne, and are supposed to look at the low-frequency signals and not only at aliased signals. In addition, we have recently found another way to address these non-neuronal LFOs, and that is with near-infrared spectroscopy. Near-infrared spectroscopy is an optical measurement which measures hemodynamic changes as fMRI, however it does so through the difference in optical properties of deoxy and oxyhemoglobin instead of the magnetic ones. The graph shows you that in the range where the optical window is, which is shaded here in darker, the absorption spectrum of lipids and other compounds of your tissue is comparably low, which allows us to penetrate non-invasively with red and near-infrared light, which you see in the 2 red bars, through the tissue to a certain depth. In addition, the absorption of deoxy and oxyhemoglobin is relatively higher in crosses, making it possible to measure both oxy and deoxyhemoglobin with 2 wavelengths. As fMRI, this is an indirect measure of neuronal activity. We have found that when we measure NIRS LFOs on the finger, the signal can be seen throughout the entire body. So we can take a measurement of the finger with NIRS, and that signal can be seen with a little time shift a few seconds later in the toe and the brain. And with the similarities of fMRI and NIRS, this gets really interesting for fMRI denoising. You see here on the slide a time course or signal measured with NIRS on the finger and a simultaneously recorded brain with fMRI. When we correlate the peripheral NIRS signal with the time course of the voxels in the brain, you get high correlations in widely spread areas of the brain. You see it in the upper pictures. And when you now shift the peripheral NIRS time course, you get other regions close by in the brain which are now correlated. And if you do it again, other close by regions. If you do that with more shift of the NIRS time course or regressor, you see how the LFOs are traveling through the entire brain and are closely following the vasculature, but which are present also in a great amount of voxels in the brain. And still remember, the video shows you voxels within the brain that are highly correlated with a signal taken from the finger. So a signal which has no brain signal in it at all. a purely non-neuronal signal. And just so you believe, we did that also with the toe, and we got similar, although slightly less good results. So summarizing, we had found a way to measure purely non-neuronal LFOs through peripheral NIRS measurements, and found that these non-neuronal LFOs are globally present, traveling through the entire body including the brain with various time lags. Coming back to our original question, are these systemic NIRS LFOs we measure related to the gold standard of low-frequency denoising, namely the respiration and cardiac variation models I introduced before? And how are these methods temporally and spatially related, and how good can they denoise actual low frequencies and not aliased signal? This is especially important since the cardiac and respiration variation models have been developed and evaluated when temporal resolution of fMRI was still at around 2 to 3 seconds. To compare low frequencies and not alias parts of the signal occurring from higher frequencies, we used the newly developed sequence which allows high temporal resolution of 0.5 TR. And to compare these methods, we had to acquire not only NIRS data but also pulse oximetry data measuring the cardiac pulsation and respiratory belt information measuring the respiration. Here is an overview of how the models were derived. The first one is the fingertip NIRS data, and you just take the various hemodynamic signals you directly get from NIRS, which is the oxy, deoxy, and total hemoglobin. Bandpass filter them and downsample them to the TR of our fMRI sequence. Then we have the heart rate variation model, HRCRF, which takes the heart rate at each TR and then convolves it with the cardiac response function developed by the same group. Similar procedure is done with the respiration variation model, RV-RRF, just taking the respiratory signal. And for the respiration volume per time, RVT method, you actually take the difference between the maxima and minima of the respiratory wave function and divide that by the time between these points. Now we have the NIRS time course and 3 other low-frequency time courses, which we want to compare and find out if they are meaningfully correlated. Meaning we need a threshold of correlation to which we can say if the correlation exceeds this threshold, we have a reliable and meaningful overlap between these signals. To see if there's a meaningful correlation between the models and our peripheral NIRS signal, we had to adjust our statistical evaluation. This is because we did 2 processing steps, namely low-pass filtering and cross-correlating, changing the random correlation distribution you see in the graphs. If I use low-pass filter and optimal delaying, just by chance with 2 completely random signals, which should have no correlation whatsoever, I end up with values such as r equals 0.3. If I wouldn't use our pre-processing steps, these same random signals would only have correlations to up to 0.08 as you see above. But our pre-processing steps change the random correlation distribution. We do not have any additional filterings. We get the statistical significance with traditional statistical methods by using our correlation and the degrees of freedom. However, if we now use low-pass filtering and optimal delay search, we change our random distribution. We broaden it with the filter and shifting the distribution right because we are selecting the optimal correlation value. So now our original threshold would be wrong, and completely random correlations would appear to be meaningfully correlated. So we have to adjust our thresholds so that our correlations do not just appear to be correlated because of the inherent random distribution, but are actually meaningful, and we found this threshold with doing Monte Carlo simulations to be around 0.3 for 1% alpha. Here you see this adjustment of the threshold, which values below accounted for spurious correlation, as we call it, represented as the dotted line in the graph. Maximum temporal correlation from the cross-correlation are on the y-axis, and the NIRS comparisons on the x-axis. NIRS, oxy, deoxy, and total hemoglobin is compared with the 3 low-frequency models, HRCRF, RV-RRF, and the RVT method, and they're all in dark colors. In addition, we use the sham condition as an additional proof for our correlation threshold, which I explained before. This sham condition is represented in the white bars. It is the correlation of the used NIRS with the same subject shifted 700 seconds in time. So we still measured a long time after the resting state and took peripheral NIRS measurements from the same subject still lying in the scanner 700 seconds after this resting state ended and compared that to the NIRS during the resting state. As you can see, our results showed mostly non-significant correlations in comparison to a sham condition. None of the correlation exceeded the meaningful correlation threshold either, so the peripheral NIRS is temporally distinct from the other methods. However, as you can see in B, in which we correlated the cardiac and respiration variation models, that these are correlated, in particular the two respiration models, suggesting that these two signals share a decent amount of commonality. This makes sense as both variations are derived from respiration. To look at the spatial distribution and the spatial overlap between the methods, we cross-correlated the regressor, for example the NIRS or the cardiac variation model HRCRF, with the fMRI BOLD data over the entire head. Then we took the maximum correlation for each voxel, and the result can be seen in the figure. We call it the maximum correlation map. You see a distribution of the various methods, including peripheral NIRS regressors on the left and cardiac and respiration variation models on the right. In a spatial comparison, we now correlate the spatial pattern of all these models. Also in the spatial correlation, there was no significant correlation between the respiration and cardiac variation models and the NIRS regressor, concluding that our signal is also spatially distinct. However, this does not mean that the peripheral NIRS LFOs we measure are not related to respiration and cardiac. However, it means that current models of LFOs account for distinct nuisances. Another important question is how much is this distinct signal containing information about fMRI? Here we show that when taking oxy and deoxyhemoglobin together, we have nearly 15% reduced variance, and that is when no alias signals are taken into account. Earlier studies with slower TRs have found variance close to 30%. To sum up, we demonstrated that the systemic LFOs we measure with NIRS are purely non-neuronal, as they can be measured in the periphery. We have found that the signals travel on a global symmetric level through the brain. We showed that these systemic LFOs are distinct from known low-frequency measurements based on respiration and cardiac, and we found that our method accounts for a large portion of non-neuronal LFOs in fMRI resting state, even more than currently used denoising methods. This purely non-neuronal signal needs to be accounted for when inferring neuronal activity, especially in resting state. What remains is, what is the signal actually? And we have not found an answer to that, but if you are interested, we have some suggestions you can read more about in the paper. We have gone further and have looked at which resting state networks are especially affected. We have looked how the signal varies with brain tissue and have evaluated how the evolving characteristic we showed can be implemented for something as the global average for denoising. And at last, we are working on the use of evolving signals as a tag for blood and made it a potential clinical method to diagnose and track moya-moya patients. Thank you very much for your interest.